Folks, this is the problem-solving portion of connected objects. So this is the problem in the slide deck, and question A is draw, it says FBDs, but we can just draw one. And I'll talk about how you can just draw one. So you still use your checklist. So everything has weight, but instead of calling this just mg, you now have to have a subscript on the masses because there's two different masses. So be careful. Sometimes I see mg, people putting the subscript on g, and g is the same for both. So the subscript goes next to the m, not next to the g. Or you could say weight 1 if you wanted to. Okay, and then this is m2g. So we got our there's no mechanical forces. There could be. I could have put a fan going left or right on here. Normal, there is one surface, so there is a normal coming from the table. These two forces are equal. So this is a boring problem, so you don't have to do your vertical for this. You can just know that that's equal to the weight. Okay, and then friction. There is friction on the surface. And there's your friction vector and T. There is one rope, so we don't need a subscript on the tension. If there were multiple ropes, we would, but this and this are the same tension. Okay, so that is the force diagram. You can put everything on the system, and you don't have to draw multiple force diagrams. However, if it helps you to also isolate this object off to the side, so you can just focus on its forces, or this object off to the side, some of my earlier worksheets will have you draw 3 force diagrams. Okay, step 2, calculate the acceleration. So the quote new formula is the acceleration of both objects is the sum of only the forces that are external and those that are parallel to the motion, divided by, the denominator is easy. Everybody brings inertia to the party. So you're just going to add up all the mass. Okay, so problem solving hint that I really like is, do I have a, yeah, highlighter. I like to highlight the motion, and that helps you visualize any force that you didn't quote, trap with the highlighter is not affecting the acceleration. So you just got to make sure that you see that, you would have trapped the friction, right? But the two forces that are perpendicular to the motion are normal and weight. Okay, is weight external? Absolutely, because the Earth's not in the system. Is the normal force external? Absolutely, because the table's not in the system. But they are perpendicular to the motion, so they can't affect it. Okay, so the other thing I would suggest draw, oh yes, you do want to draw, is the acceleration of each object. So what is a little bit goofy is that anytime you have a pulley, what that does is it physically rotates your axis system. So the direction of acceleration is defined as positive. So you don't have to draw the axis systems unless it helps you do the problem. But this object has a standard horizontal and vertical axis. This object, its axis is rotated. So down is horizontal, and we don't have anything left and right, but that would be vertical. Okay, so super quickly, what some people like to do, I personally don't, but I'm not going to yuck your yum. Some people like to kind of lay this out all on one line and redraw the force diagram this way so they can see all the forces. Okay, so as long as you do this here so you can see the true direction of forces, if that helps you, then by all means do that. Okay, so let's calculate the acceleration. So the acceleration is any force that is in the positive direction, or, is positive, duh. So it's going to be m1g minus tension. Come around here. Oh, that tension is positive. Plus tension, We're going to ignore normal and this weight because they're perpendicular to the motion, minus friction all over M1 plus M2. Okay, so I broke my rule. Oh, sorry. We only looked at external forces. No, we did the forces parallel to the motion, but I did do the two internal forces, which are the tensions, because I want you once to see, oh, look, plus T minus T. Those are always going to cancel by Newton's third law. Okay, so you can do it. It's not wrong, but they're always going to cancel. So that's why we don't include them in the overall acceleration. Okay, so then I already did the numbers out. The weight of the hanging block is 26.46 newtons. And in your you do have to show work for this. So miscellaneous F equals mu n. Technically, I would call this N2. There's only one normal, says okay. So 0.10. What you don't have to show anymore is if it's a boring problem, you can just say that you know the normal is the weight of that block. Okay, so friction is super small. It's not reducing the acceleration by much at all. And the denominator is going to be always all of the mass. Okay, so what you get is 5.77 meters per second squared. Okay, so check that we drew the force diagram, we found the acceleration. Check your work. If it is powered by gravity and there's no fans or jetpacks or whatever, this should always be less than 9.8, right? Because this object by itself wants to accelerate at 9.8. But because this has inertia, that is literally what is making the rope molecule stress. This is trying to stay at rest. This is trying to fall at 9.8. And that tension, yuck, 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 causes tension in the rope. Okay. Which is going to slow, like if you look at this, it's not in free fall. The tension is reducing the acceleration. Okay. So that's a hint to check your work. Okay. So last part, and then I have one more slide with some hints. Now we want to find the tension. There is no way to find the tension if you include both of these objects in your system, because then it's internal and it's going to cancel. Okay, so to find the tension, you isolate either the 2.7 or the 1.6 kilogram block. It doesn't matter which, and that's a great way to check your work, just like, collisions, testing both objects' position functions. Okay, so clearly, ideally choose whichever one is easier. In this case, not clear. They both have two forces, all right? But the point is you're going to focus on an individual object to find the internal forces. Okay, so to find the tension, now we are going to isolate, doesn't matter, this, let's say this object, and then we're going to do some of the, you already know how to do this, some of the forces equals MA. But again, what's different is, normally we would have said tension was positive and weight was negative. With the direction of acceleration is positive. So defining this as our system, the Earth is outside the system. That's an external force. The tension, the tension caused by this object is outside the system. So that's an outside force, equals just M1A, because we're only focusing on M1. Okay, so that object's weight is 26.46 newtons minus tension, that's what we're looking for, equals 26.46 times, that's why we look at the whole system first to find A, and A was 5.77. Okay, sorry, I went on autopilot and I typed in the weight, not the mass, so can't remember if I did that on or off video, but fix that if that's a mistake. Okay, so the weight minus tension equals MA. A is positive because it is accelerating down, and down is positive. When you solve this for tension, you get the tension is 10.88 newtons. So again, that makes sense because it's got to be less than the weight, because the weight is winning, it's accelerating down. Okay, you could also check your work by doing sigma F equals MA for this object, and you would say tension minus friction equals its mass times the acceleration. So tension minus 1.66 equals 9.232 and add 1.66 to both sides, and you get 10.89. Okay, so weight's got to be bigger than tension. Tension's got to be bigger than friction in order for everything to accelerate in the direction that we know they are. Okay, you don't have to do both objects, but it's a great way to check your work. All right, almost done. Thanks for listening. And then, so this is the last slide. I already said this, but wanted this for people to just reviewing the slide deck. You have got to have subscripts on your masses, and again, say M1G, not MG1. Okay, unless you want to say MG parentheses 1, but I don't. This is more standard. Okay, and if there are multiple tensions, your tensions need subscripts. I don't think that's a problem. You've seen that before. And then if the system is powered by gravity, the acceleration must be less than 9.8 meters per second squared. Okay, all right, that is it. And this is the last lecture for connected objects. So we're just going to practice. Thanks for listening. See you in class.